Hello, and welcome to our next part of the discussion of material in sections 10.5 and 10.6 in our calculus textbook. I've got two more examples to work for you in this video of finding intervals of convergence for power series. First example, summation n equals 0 to infinity minus 1 to the n, x minus 3 to the nth power over 4 to the n. So as we mentioned last time, we want to use the ratio test to help us do this with the additional help from looking at the endpoints that we get of the interval we get individually. So as before, I'm going to write out a sub n and a sub n plus 1. So rho is going to be the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. As I've been doing, I'm going to write this immediately as a product of fractions. And hopefully we can see that there's going to be a lot of cancellation going on here right away. So 4 to the n is going to cancel with this, leaving a 4. X minus 3 to the n plus 1 is going to cancel with that, leaving an x minus 3. And minus 1 to the n plus 1 is going to cancel, just leaving a minus 1. And so I get minus 1 times x minus 3 over 4. Well, the absolute value of the opposite of an expression is just that expression, and so this is going to be the limit as n goes to infinity of the absolute value of x minus 3 over 4. And there's no n here, and so this is our limit. This is just a constant. The limit of a constant is just a constant. And so the series, the power series, converges when the absolute value of x minus 3 over 4 is less than 1. Well, again, I can write this in this way, and then I'm a big fan of converting this into an inequality that doesn't involve absolute value. And so if x minus 3 in absolute value is less than 4, that means that the expression inside the absolute value symbols, x minus 3 in this case, it must be caught between negative 4 and 4, and then I can add 3 everywhere and get that x has to be between negative 1 and 7. So that the interval of convergence definitely includes all the numbers between negative 1 and 7, but because the ratio test is inconclusive when rho is equal to 1, I need to check the endpoints separately. And so when x is negative 1, I get summation n equals 0 to infinity minus 1 to the n, negative 1 minus 3 to the n over 4 to the n, negative 1 minus 3 is minus 4 to the n over 4 to the n. And minus 1 to the n times minus 4 to the n is just 4 to the n. So I get summation n equals 0 to infinity 1. Well, the limit of if the general term is 1, the limit as n goes to infinity of 1 is equal to 1, which is not 0. So this diverges by the nth term divergence test. So notice that for testing our endpoints, we're going back and relying on test information that we looked at previously. So for x equals 7, I get summation n equals 0 to infinity minus 1 to the n 7 minus 3 to the n over 4 to the n. So I get minus 1 to the n, 4 to the n over 4 to the n. That cancels, leaving me with just this. Well, our general term is minus 1 to the n. Limit as n goes to infinity of minus 1 to the n. This alternates between plus 1 and minus 1. And so this limit does not exist. And so again, the series diverges by the nth term divergence test. And so if it diverges at both of these endpoints, my interval of convergence is going to be simply the open interval from minus 1 to 7. Let's look at one more example. I've used a little more space than I would have liked. Summation n equals 0 to infinity x to the n over n factorial. A sub n is x to the n over n factorial. A sub n plus 1 is x to the n plus 1 over n plus 1 factorial. And so rho is going to be the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. That's going to be the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Well, remember what we've seen in the past. We can write x to the n plus 1 as x times x to the n. I can write n plus 1 factorial as n plus 1 times n factorial. So I get lots of cancellation here. I get the limit as n goes to infinity of the absolute value of x over n plus 1. Well, what do we see? As n gets big, n plus 1 is going to get really, really big. And so I can think about this. I'm abusing the notation a little bit. The limit is 0. But I can think about this as 0 times the absolute value of x. Well, when is 0 times the absolute value of x less than 1? Well, this product is always 0. And so the answer is for all values of x. And so there are no endpoints to check this time. We just get to say that the interval of convergence is the set of all real numbers. It goes from minus infinity to infinity. We will explore this series in much more detail when we get to section 10.8 in our text. So we look forward to that.